about file format. We don't really talk about we don't really bridge that gap with what does it mean to optimize files for the cloud. What are the core challenges? Why is it different from optimizing for on-prem? Okay. So I like to break down the problem of file access into just 3 pieces. I need to figure out which bytes I need to read. Sorry, I should step back and say I'm talking about partial file access. So I want to read a piece of a file. I don't want to read the whole thing. So if I have that and I want to get a little bit of data, if I have a file and I want to get a little bit of data out of it, how do I get it? I need to figure out which byte in the file, which byte ranges I need to read. I need to actually read them. And then I need to somehow interpret them. In a lot of cases, that means decompressing them or just putting them into a programmatic array so that I can do something with them. And so I break these down into locating, reading, and translating. So to kind of frame the question of cloud optimization, I want to look at what performance looks like on a local hard drive and then look at what it looks like in a cloud object store for really I focus on the first 2 pieces because that's really where cloud optimization happens, access optimization. So let's look at that access performance. On a hard drive, the important takeaway here is that reads are really cheap. You can perform a lot of small reads and you're not going to notice it if you're churning away and reading a lot of little things because latency is very low. For SSDs in particular, it's extremely low. Throughput's very high. You can skip around a file like crazy, and unless it's you're doing huge numbers of reads, like in the thousands to millions of reads, you're not even going to notice it. And so a consequence there is that if you're going to optimize for accessing from a hard drive, you don't really care about the number of reads as much as you care about getting precisely the data that you need. By contrast, in the cloud, it just shifts the numbers on these latency and throughput values. So latency from an object store is very high. That number there is about 700 times more than what you would see from reading from a hard drive. And the throughput is also very high. It's actually, in many cases, higher than what you get off of a hard drive. And the consequence there, if you think about it, is that making lots of small reads is very expensive. Whereas because you can pull so many bytes back so quickly, getting too much data and throwing some of it away is actually pretty cheap. So it shifts the math. And so cloud optimized, the way that I like to think about it is you want to fetch a lot of data in a small number of reads. And then you're operating at a scale where you can't just fetch everything, right? Like the smallest number of reads is to just grab the whole file, right? But you're dealing with many megs, many gigs, terabytes, petabytes. And so you don't want to just fetch everything, but you also don't want to be skipping around and doing a lot of extra work reading things. So how do we cloud optimize things? There's some easy wins to be had. This is something that almost all cloud optimized formats that I've seen do, which is to somehow group file metadata, preview information, overviews into a single location so that they can be read in one or a small number of reads. Instead of having to make 20, 30 different reads just to do that locate step that I talked about, you do a single read and you can figure out what else you need to read to get the data you're interested in. And for us, as I mentioned up front, we're doing that using the DMR++ file, which is extracting all of the file metadata and the byte offsets within the file into a separate file. We can read the DMR++ in one go, and then we can skip straight to where we are interested in within the file. There's some harder work to be done on cloud optimization that I don't want to get too much into, but it is important. Pieces of it are important for the work that we did, so I want to introduce it here. The harder work, I think, is this data locality question. If you think about it, a lot of our data sets in the very simplest case are 3-dimensional, right? Latitudes, longitudes, and time. And on disk, everything's one-dimensional. Each byte in a file is identified by an offset from the start of the file. And so you're necessarily collapsing a higher number of dimensions down to a lower number of dimensions, and there's going to be trade-offs there. And particularly if you're optimizing for analysis in one dimension, you're probably hurting analysis in another dimension. In practice, I think you could imagine this trade-off using this 2D example here. You write the file just going across longitude values, and then you go down the latitude values, writing out the file. And you can imagine if you have a use case that goes long and short in the longitude direction, that you can actually read that all in one go, in one read. But if you have a use case that is tall and skinny, and you've written the file out this way, then you're going to be making a large number of reads in order to read the file. So it's important to kind of understand the sort of file structure piece. And there's no real one-size-fits-all answer here. Another important concept sitting in all this is the concept of chunking. So you can imagine that each of these boxes here is, instead of being just one data value, that it's actually a small window of the data that's read all at once. And so then you can have questions swirling about, well, how big should I make these boxes so that people aren't reading too much data versus too little data when they're fetching their area of interest? Should I make them skinnier in one direction or taller in another dimension? Those kinds of questions all come up when you're optimizing for file access. And that's about all I'm going to say about chunking. I think people can and have talked about optimizing chunk sizes for hours on end. But I'm just going to leave it here and move on to what I actually did. Okay, so talking specifics about the demo that I was showing before. This is a representation, I showed this picture earlier, a representation of a typical netcdf4 data file that we might be serving from our archive. It has a bunch of metadata up front, maybe some arrays that tell us where points fall within each dimension on the Earth, and then several data variables. And then the partial access use case looks something like this. I don't want everything. I want data from a single variable in a given area. And so this case is the conterminous US. Showed the Great Lakes before, but that'd be a little small in the picture. And then in order to get at that using just standard netcdf or HDF5 libraries, I need some other pieces of information within the file. I might have to do several reads to get at where do I need to look within this file to get the area of interest. And this is really what I alluded to earlier, which is that I don't want to make a lot of small reads just to figure out what else I need to read, because that's just very expensive in the cloud. And that's where the OPeNDAP DMR++ comes in. They're extracting all that information. I can read it in one shot, and then I know exactly where to look within the file. So the only question from there is how to actually read the data. I can easily fetch this using HTTP or Perl or some library, get the DMR++, but how do we actually get the bytes out of the data file? And luckily, there was some prior art here. It turns out the USGS and the HDF group had done some work using metadata in a format that was built for ZAR that lets the ZAR library read netcdf4 files as though they were ZAR files. They also showed that doing this, reading netcdf4 files that way, had comparable performance to reading native ZAR S3 data. So it's quite fast to use the ZAR library to read netcdf4 data. And it wasn't too hard to imagine that I could use that same technique, and instead of reading ZAR metadata, I could read this OPeNDAP DMR++ and kind of present that to ZAR as though it were its own native format. So that's what this ZAR EOS store that you saw in the demo is. ZAR is actually a really nicely built piece of software, and it's supports multiple storage backends. So you can store ZAR in S3, you can store it in zip files, you can store it in a database. And so what we're doing is we're presenting a store that is stored in the cloud in netcdf4 and DMR++ format. And the ZAR Python library just reads it like it's normal ZAR data. Behind the scenes, we're just doing some straightforward conversions. When it asks for a chunk of data, we figure out what byte range that is and pull it back from the data that we have in the cloud. So that actually worked very well out of the box, but there were some areas that we could improve on it. For one, and this is kind of specific to us, there's a little bit of shuffling that goes around up front between the aforementioned authentication that we do, but also we have a canonical URL that gets translated into a pre-signed S3 URL, just some HTTP back and forth that is a little expensive for the first request. With very slight changes, though, we can make it so that we pay that price once, and then once we've gone through that sort of handshaking, we have a pre-signed S3 URL, and all of our subsequent requests are going straight to S3 over HTTPS and working just about as quickly as they can. So also in many cases, the netcdf4 files that we have aren't optimized internally for cloud access, like I talked about in the first section. So they were often packaged for on-prem and then moved to the cloud because we're in kind of this transitional period. I think a lot of us are in this boat. So they tended to prefer the many small and precise data reads rather than a few larger reads. So there are some things that we could do here, but it turned out, as of last year, if you asked the ZAR library for a file like this, where you wanted to read a bunch of little pieces of the file, it would ask for them in sequence one at a time until it got all of them, and it would wait for the prior one to finish before the next one went. There was no parallelism or anything like that. So we did work with the ZAR project and implemented a proof of concept that was in, I guess, last year. I presented similar information. It was in an experimental state back then, but it has since been merged to the ZAR library. And basically what it does is the ZAR library, if your storage supports it, instead of saying, give me this piece, give me this piece, give me this piece, it'll say, I'm about to ask for all of these pieces of the file. Could you please give them to me? And then we can be a little smarter in our library about how we are actually fetching the data itself. And so that let us make a few more optimizations. The one optimization that we made was to recognize that we're about to ask for a kilobyte here, and then the next kilobyte, and the next kilobyte, the next kilobyte. Why don't we just ask for the 2 megs that we need, whatever it happens to be, in one request, and then break it up after we fetch it, rather than making a bunch of small requests. That effectively turns what was on the previous slide, 100 requests, into about 7 requests here. And it makes a huge difference when we have these small chunk sizes. Effectively, it just erases a dimension in many cases where we had been dealing with iterating across latitudes and longitudes. Now we're just dealing with iterating across latitudes. And we are performing significantly fewer requests, which is, again, the way that you want to do things for cloud optimization. And then the other optimization that we made is maybe the first one that jumps to mind for a lot of people, which is that we could also just ask for all these byte ranges in parallel. We grab the first one, we cache a bunch of HTTP information, get that pre-signed URL, and then we just fan out the requests. And that turns out to be a lot faster too, and, kind of because it groups all the latency into one. You pay the latency penalty once instead of many times. Not yet implemented optimization that is definitely coming and can be easily worked around in code today is that we should be caching the results that we get back, so that if you ask for the same ranges twice, that you don't actually refetch the data. I mentioned this before during the demo, but this is all open source. This is the GitHub link, /NASA/zar-eosdist-store. It's also on PyPy, so you can pip install zar-eosdist-store to try it out. It works for much of the NASA EOSDIS netcdf4 data that is in cloud storage. So where does that actually leave us? I think more than a single library implementation, I think there are some underlying techniques that are important here. If you can combine smaller reads into fewer larger reads, if you can skip expensive network actions like not re-authenticating every time, not getting redirected every time, and if you can parallelize your reads, then the underlying storage mechanism actually isn't nearly as important as it might seem. And in our case, and maybe in some cases, you might find that netcdf4 ends up being your favorite cloud optimized data format. That is all I have. Open to any questions or comments.
Thanks a lot, Patrick. That was fantastic. That was fantastic.
Thank you.
Any questions?
Hey, Patrick, this is Ted Haberman. How are you?
Hi, Ted. How are you?
Good. A couple questions. You mentioned ZAR reading from a database.
Yeah.
I'll give you the two questions, then you can answer. You know, do you have any thoughts on reading DMR++? You know, the basically the chunk offsets from a database instead of from, I don't know if you guys are still using XML for DMR++ or JSON, whatever, but I've got a situation where I have a file with 1.3 million objects in it. And the idea of a JSON file with 1.3 million little dictionaries doesn't seem very happy to me. And the other question I have is, one of the pieces that I haven't seen discussed very much in this ZAR-like chunking kind of approach is data sets with a lot of attributes. I have a bunch of data sets that have a lot of attributes, and attributes are not stored contiguously in HDF. And so I'm wondering what you're thinking about attributes.
Right. So on the first question, I maybe kick that over to James, because I think I have recognized we've had some cases of where we'd see it come up as a very large file with very tiny chunk sizes. Like I've seen a case of over a gig for the file, and then the chunks are 10 kilobytes. And that works out to be a heck of a lot of XML in the DMR++. And that, you know, can dominate the performance of actually reading the whole file. This work is more focused on dealing with what we have, like working with the files that are already out there versus actually determining what the structure should look like. So I don't know if James maybe has any thoughts on, you know, using a database or something similar to store similar information for the DMR++.
Yeah. So we have been talking a lot inside OPeNDAP about just what to do with the really, really large DMR++ files. And Ted, your concerns are exactly ours, that when you get into ones with 1 million or so elements in them, whether it's XML or JSON, it almost doesn't matter. The performance is always appallingly poor. And so, and of course, one of the things that we can do with DMR++ is that we can aggregate things really effectively. But those DMR++ files become even larger, right? Because now you have 1,000 really large things represented in one file. So a database is almost certainly the way to go. And then the real question is, do we want to try to use a relational database because that's existing technology and it's really accessible to people? Or do we want to try to use something like DynamoDB, which is basically a key value store? It's already in the cloud, and it can be easily replicated with other non-cloud technologies. So you can just say, oh, we got this key value thing, and we're going to get the stuff from that. those are things to look at, and I think those are really important things, because it's pretty obvious that that this is a useful technique given the amount of commitment that NASA has already made to formats like NetCDF4, which, as we all know, is under the hood HDF5. So
now, I think
sorry.
one important aspect of it that there's a piece of that of benefit from XML that I wouldn't want to lose, which is that I, as a fully external consumer, was able to make use of it in a new and interesting way, that if we were to squirrel it away behind a database that was closed off to public access, that might not have been possible. And so I think maintaining that sort of open nature of whatever the solution is would be very important here. In terms of the question about attributes, I'd say that this work was a lot more focused on getting into the multi-dimensional array data. I think my understanding is that the attributes themselves would be also present in the metadata, but it's been a lot less of the focus for this effort, just by nature of how the files that we work with have been structured. So maybe there's more to look at there.
Right. Well,
are there any other
kind of
questions? I think I'm.
Oh, Ed Armstrong has his hand up. Ed, do you want to pop off mute?
Yes, I did. I did have my hand up. Quick question for Patrick. Maybe I'm not understanding things quite correctly, but I wanted to ask you about, would it be possible, instead of using the OPeNDAP DMR response, would it be possible to use a query directly to the CMR, the UMM variable record for that, kind of structure and logistical information?
So right now, today, the CMR does, CMR being NASA's common metadata repository where we store metadata about various file holdings. It has a lot of the variable information. The important piece that the DMR++ adds that is not yet in CMR and maybe not ever in CMR, I don't know, is the actual byte offsets of the chunks within the files. I think getting at that was really the goal that allowed this to work.
Got it. Okay, I see. So it's the byte offsets. It's kind of the key of using why you're using the OPeNDAP DMR. Yeah. Okay, thank you.
Yeah.
Any other questions for Patrick? I see there's some things in the chat, but they've been effectively answered by other folks. Well done.
Okay. And I'd be happy to engage offline with anyone in the chat, or you can reach out to me afterwards. But I'll pass it on so I don't eat up too much of our session here.
Great.
Thank you all.
No worries. Really interesting stuff, Patrick. Thanks a lot. Bob and Roy, are you guys ready to go?
I hope so. Can you hear me now?
Yes, we can. That's wonderful. Thanks very much.
And can you see my slides?
I can see your slides. Yeah.
Excellent. So here we go. Almost. Okay, so I'm going to be talking about running Erdap in the cloud. First, I'm going to tell you a little about Erdap for the people who aren't familiar with it. Erdap is a data server. It's reusable, free, and open source software. Erdap has been installed by more than 90 organizations in at least 14 countries and is on NOAA's list of recommended data servers. The Erdap homepage, which is shown here, has a description of Erdap on the left and several ways to search for data sets on the right. So if I enter SST in the search box, I get a list of relevant data sets with the most relevant at the top. All of the search options lead to a list of data sets which shows ways that you can access the data set, which are on the left, the data set title in the center, and some information about the data set on the right. The data link for each of those data sets leads to an OPeNDAP style data access form so that you can request a subset of the data. A unique feature of Erdap is that you can enter the actual latitude, longitude, and time values, or whatever the dimensions are, not just the index values. Another feature of Erdap is that you can specify the response file type from any of 20 different file types in order to get the data in a format that's easiest for you to work with. There are also make graph web pages for all data sets, so you can create custom graphs and maps. And if the data is stored in files, you can download the entire files. The impetus for the creation of Erdap was my belief that from a user standpoint, finding data and downloading it into your favorite client software is too hard. These were issues when I started 13 years ago, and there's still problems today. So Erdap is designed to solve these problems and make it much easier to get data into your favorite client software. So the first problem is that most data servers lack a search system. It's hard to find data sets of interest. Different data servers use different request protocols. Different data servers return data in different file formats, and it's often not the format you want. And different data sets have time formatted in different ways, which is difficult then to compare data from different data sets. And most data sets have insufficient metadata. So without Erdap, there are lots of sources of data on the web and now in the cloud. And there are lots of clients working with each of those types of servers. But there isn't a lot of ways to get data from a specific type of data server into the file format that you want or into the client that you want. So with Erdap acting as a middleman, you can, it works with the existing world of different types of data servers who are now at the cloud, and also allows you to get data into the favorite client software of your choice. So acting as a middleman allows Erdap to improve the metadata, generate ISO 19115 metadata, standardize the format of time data, provide a unified way to search for data sets of interest, and offers a standard way to request data from any data set and specify the file format. So hopefully it solved the problems that I identified earlier and makes life easier for data providers and users. And it is in line with the FAIR principles: findable, accessible, interoperable, and reusable. It's important to note that Erdap's web applications, which are web pages with a form designed for human use, are built on top of Erdap's web services, which are all RESTful web services where a single request URL specifies an entire request. The services are more useful for computer-to-computer requests and work, but the web applications are also useful if a human wants to just download a chunk of data for some other purpose. Fortunately, these two things work together. As I said, Erdap's web applications themselves call Erdap's underlying web services. So now we'll get to the real point of this session and the point of this talk, which is the cloud and how Erdap works with the cloud. Well, the cloud. People talk about the cloud as if it's one thing, but it isn't. There are different companies and they offer different services. So Microsoft Cloud offers many things, but including Kubernetes, SQL, a lot of AI options, and all kinds of other things. Google's Cloud also does Kubernetes, SQL, AI, although it's different, and BigQuery and some other services. And Amazon's Cloud adds Kubernetes SQL AI of its own type, EC2, which we'll talk about in a minute, and different storage systems. But it is Amazon's cloud that NASA and NOAA are primarily using. There are some uses of Google's cloud and Microsoft's cloud, but for the most part, when we talk about the cloud, this session and I will be talking about Amazon's cloud, and specifically EC2, which is Amazon's system for renting time on a computer, or as they say, a compute instance, and S3, which is one of Amazon's systems for storing data It was available early on, and it's relatively cheap. It's widely used, mostly because it is cheaper than EBS, Elastic Block Store, which is, EBS is very much like a hard drive or a RAID attached to your computer. NASA and NOAA make extensive use of S3. NOAA's big data project is on S3. And so, again, I'm going to be talking about EC2 and S3. If everyone used EBS, we wouldn't be having this session because there would be no problem to solve, in a sense, because EBS works like a hard drive that's locally attached, and a lot of the problems associated that we're going to be talking about are associated with S3. S3 does not work the same as storing files on a local hard drive. It's a bucket. It has buckets and objects in those buckets. And so what's the trouble with Amazon's S3? Well, the trouble is that software just doesn't just work as it did before. If there wasn't a problem, we wouldn't be having this session. You have to use the OZ API. It's true, you can use URLs in some cases for public data, but in general, you must use the OZ application program interface to access data from it. A big difference is that S3 is far away, not local, so this induces the lag that Patrick was talking about. And S3 only offers file level access versus block level access that you can get from a local hard drive. What that means is that you can only access entire files. There are exceptions to this. You can do a byte range request, but it's quite inefficient. And so this is the reason that groups like Patrick's split a file up into chunks, and each chunk can then be read. And so you're accessing the individual chunks, not the entire file. So from Erdap's point of view, S3 file level access is fine if you're reading from an ASCII CSV file because you're going to be processing it in a streaming manner. But the problem is with binary files, netcdf and hdf files, where the file is large, and if you can only access the entire file, then access is slower. Although, as Patrick said, it's the initial start of the data getting to the computer, to your computer, but the actual throughput is quite fast. I'll make an analogy of getting groceries from a refrigerator versus a store. If you're accessing data from a local disk drive or from a RAID on a server, it's like accessing food from a refrigerator. Access is fast, easy, efficient, and free. And it's fine grain too. You can pour one glass of orange juice from a container. But accessing data from S3 is like going to a store. Access is slow. You have to drive there and back. And it's not fine grained. You have to buy a whole container of orange juice. And it's costly. You have to pay for storage, although not for access if you're in the cloud. So these differences have led to various solutions like Hyrax's solution, ZAR, cloud optimized geotiffs, caching, etc. If it wasn't trouble, we wouldn't need these solutions, and we wouldn't be having this session to talk about the problems and the solutions. So Erdap's solutions for working with OZ, EC2, and S3. Erdap is a Java application, so it uses the OZ SDK for Java version 2. It can't use ZAR, so that's an unfortunate thing. That may change. I hear Unidata is working on a ZAR for Java, but it isn't there yet. And so as I said before, for tabular ASCII files, Erdap can just stream the file. The lag is unfortunate, but it's reasonable. And then once the data starts arriving at the server, it comes quite fast, and so it can be processed right away as it comes in. So that works pretty well for that type of file. But for gridded and binary files, Erdap uses a cache system. So there's 2 settings for each data set. One is cache from URL. That lets you specify the URL where the data is stored. And in this case, you will specify the object name in the S3 bucket. In its HTTP form, there's a way of specifying that location as a URL. Erdap notices, oh, this is a specially formatted URL, and knows that it's a S3 source, and therefore uses the Oz SDK for Java to read files from that in order to bring files into the cache, and then you can specify the cache size with cache size in gigabytes, that setting there. So there's a penalty for the first use of a given file, but then it's super fast because Erdap has a locally cached copy of the file. Different solutions can be offered to the problem of S3. They are better or worse for different scenarios. So, but the good news is that all of the solutions work for all of the scenarios. It's just that they're better or worse. So I suspect that for one-time use, Hyrax's solution and ZAR are faster. From a geospatial subset through time scenario, Hyrax's solution and ZAR are faster. So that's kind of the perfect setting for those where you just need a small chunk of data from each file, but you're reading it from several different files. Those systems that are good for selecting small subsets are particularly good for that scenario. And Erdap is therefore not so good at that scenario. But Erdap is good for 2 or more uses of a given file, and because it has that local copy of the file. So in a lot of things in Erdap are repeated use. For example, if you're making a series of graphs, a user using Make a Graph will be accessing the data from a given file repeatedly, perhaps for a slightly different geographic range. So those types of requests are faster in Erdap. So there are at least some scenarios where Erdap's solution works quite well, but there are certainly solutions where it's suboptimal. But that's just the way it is. You optimize for one thing or you optimize for something else. So that's my talk with slides. You can read about Erdap and try it out at that URL. You can download and install Erdap if you want to be a data provider. And there's my email if you want to contact me. Should I go ahead and do Roy's presentation now?
I think that would be great. Yes, let's segue right into that.
Okay, let's see if this actually works. And if you can hear it, I'm worried that the audio won't work for this, but we'll give it a try. Can you hear that?
I can't quite hear anything. No.
How's that?
We can barely hear that audio. It's not really audible.
Okay, I can't make it any louder, so I think that this is not going to work. So probably just move on.
Is it a file that you're playing, Bob?
It's a file.
Um,
and since I'm using, I put my mic right up to it and I have the volumes turned up, but that's as loud as I can get. It's a quiet audio file. So I think that's not going to work out. Sorry.
Is it a shareable file such that we could share it with the group, or something that you could send me and I can put it somewhere to share?
Sure. If you send me an email, I'll send you the file.
Great. I will do that.
Well, but let's go right into some questions. I noticed that Jolie made a comment that Erdap is pure Java, and that there's an HDF5 pure Java S3 reader. That's pretty interesting. Joe, do you have any comments about that? And are there any other questions for Bob?
Well, I'll just say Erdap is using the netcdf Java library, which reads from netcdf4 and HDF5 files. So I'm relying on that to read those files.
Okay, right. And does that library also contains the code that reads from S3? Sean Arm says it's capable of reading from S3.
I am aware of that, but Erdap does not use any of the netcdf Java cloud-related features. Those were added very recently.
Okay.
I haven't explored them.
Okay.
I don't know what to say. Erdap has the caching system that works with Oz S3.
Right. Okay, so Erdap has its own caching system. So Ted is trying to raise his hand. So Ted, do you have a question?
Yeah, Bob. Thanks for that talk. Interesting. One thing that you said was that I'm confused by was you said in S3 you need to read the whole file if you're trying to read a file, and I think that most of the current work that I'm aware of shows that reading chunks from files, like Pat talked about last time, is completely equivalent in performance with reading the whole file, and you said that, I believe you said that was inefficient. I'm wondering what data you have that supports that statement.
I'm just saying, as I said in the talk, that there are scenarios where one is good and the other is good, and as Patrick showed, there's a latency to get the first byte, but throughput is good once you get that first byte. There's a latency because the S3 is further away than a hard drive. So as Patrick said, fetching lots of data in a small number of reads is the optimal thing to do. Erdap just takes that to an extreme and makes one read in order to fetch a lot of data, the whole file. Now, as I said, there are that optimizes for certain scenarios and does not optimize for other scenarios. But if what you're implying is the opposite of what Patrick said, which is making lots, and which is what a lot of people do with ZAR and these other things, that they make lots of data reads, which is, as Patrick said, not the optimal thing to do, because you're incurring the lag, the latency penalty multiple times unless you do it in parallel. But often you can't do it in parallel because it's the first read that gets you the information about the DMR information about where things are in the file. So you're incurring multiple lag penalties. Erdap seeks to avoid that by just making one read. Admittedly, for a large file, there's then a penalty because you have to wait for the entire file. That's all I'm saying, is that there are trade-offs for different scenarios. One advantage to Erdap scenario is that you can work with the original files, netcdf and HDF files as is without storing them in a cloud optimized format. Although, again, as Patrick said, with his technique, it becomes very efficient to read HDF directly that way, in a ZAR-like way.
Yeah, I think I would sort of add to that there is a kind of a tipping point If you only wanted 1% of a file, it might be okay to go grab a couple of chunks. But once you want about half the file, it's probably faster to just grab the whole thing. And Patrick and I have hemmed and hawed about that. Exactly where is that tipping point and can we calculate it? And so I definitely, if you want the whole, just grab the whole thing. There's another point that's worth making as well. And that's that while the techniques that we've developed, that Patrick has talked about, and that the DMR++ addresses works great for anything so long as it's stored ultimately in HDF5, what about all those binary formats that are not HDF5? And in that case, you have to basically go through and figure out how to get this chunk information. That is to say, the byte locations and offsets. You have to figure out how to get that. It turns out, well, anyways, there's a story there. But anyways, I completely agree that there are plenty of situations where you just want to get the whole file, and it's probably faster to do it that way. And then there's other situations that Patrick talked about where it's clearly optimal to get just parts of the file. So, it would be great if there was a one-size-fits-all solution here, but there isn't really. But Ted, you have a follow-up question.
Well, yeah, I mean, I assume you're talking about getting the whole file onto an EC2 somewhere running on the cloud. If you're talking about downloading the whole file, not only is it going to be slow, but it's going to be expensive because of egress. So now you're talking about running a pretty beefy EC2 instance.
Yeah, I'm talking about running an EC2 instance. I'm talking about running Erdap in the cloud. That was the title of the talk.
Yeah, definitely. And I was talking about that as well. I'm thinking about just pulling the whole thing into an EC2 or an EBS or EFS volume and working with it there. So. Classic move, classic neophyte Zoom move. I was muted. Are there more questions?
I have one.
Okay.
So actually, I was just going to make an observation. The optimization that we ended up doing is there is this problem, right, where the files were created in a world where disk space was precious. And so they're chunked in a way that makes them compress really well and blah, blah, blah. And there's a zillion chunks and it's not very efficient. You're absolutely right. Can't make all those requests, right? That costs, even if they're parallel, it costs. But what we ended up doing is looking at the data in the actual data and saying, well, there's actually these super chunks that are made up of hundreds of other chunks that are contiguous, And so if we restrict our requests to these contiguous blocks of required content, then instead of making 100 requests, we can make one. But we might end up making 5 to get a variable, but that's better than 500 or 1,000. And that seems to work pretty good. So I think that there's places where these existing files that you can write optimizations that are smart about how many things you actually get. And don't be fooled by some of this latency time too, because we definitely have seen that S3 is not the same from one request to the next. And once you've surfaced an object, that's the way we think about it. Like once you've requested something for an object, like right now, going back to that object is a lot less expensive. You come back in a few hours, it'll be expensive again. But there's this weird behavior on S3 where stuff seems to sync. And when you've surfaced it, it's pretty fast once it's there. And that's all I have to say.
Yeah, that's a good point, and I sort of forgot to mention that. If we don't have any more questions, thanks a lot, Bob.
I have a question. Actually, I think both I and Alex have had the same question, and that is, we talked about one size doesn't necessarily fit all. So Bob, I'm kind of wondering what size files are we typically talking about for Erdap? At what point would a file be too large that you would be comfortable with the approach of pulling the whole file out?
I'm not going to answer it quite that way. I just say the files are the files, and there are scenarios where the caching approach works better, and scenarios where it works worse. And you're absolutely right. If the larger the file is, And the smaller the amount of data you want from it, then the worse this solution is. Absolutely. But if you want repeated grabbing of data from a given file, then that penalty lessens. So I think everyone's looking for this perfect solution, and I'm saying that I don't think there is a perfect solution. I think there are scenarios, there are certain types of requests that come into Erdap or HIRAX, and for those requests, a given approach, either caching or DMR++ or whatever, is going to work better or worse. But as I said, all of the solutions work for all of the scenarios. It's just that some solutions work better for some scenarios than others.
True. Okay, if there are no more questions, and remember, this is a relatively informal gathering, so we don't need to be too precise about that. I'll maybe run through a couple of quick slides that are kind of a technical background on DMR++, and then maybe I'll get a chance to show you some stuff. I don't want my part of this to dominate it, because I really think that we've had, both from Patrick and Bob, we've had some really great information here. But I do have a couple of quick slides to go through. So
James, quick thing. You might want to, you could not share your video while you're sharing your slides, because you've got a little bit of a lag. So maybe just turn your video off while you're sharing your slides.
Gotcha. I'm doing it.
Right.
Yeah. So let's see. Okay. So this is going to take me a moment to figure out. I'm sorry. You know, it's hard to imagine. We've been doing this for what, months now, but all of a sudden it just fails. Okay, PowerPoint. Wait a second. My apologies. It's proving to be difficult.
No.
As in, I have to quit and rejoin. So I'm sorry.
No worries. Let's see. I'm keeping an eye on when James gets back. Oh, there we go.
Yep, I'm back. Sorry about that.
No worries.
You know the deal. It's the you have to share your screen, and it's very secure now.
Okay. All right. Looks good.
Yeah. Okay. So I'm going to talk about data optimization in the cloud, and I'm going to run through this pretty quickly because I have some other demos that I want to show, and I want to show them. So what is cloud optimized and why do we care? So these slides are going to look a lot like Patrick's, because Patrick is a co-author of this presentation as well. But the real idea is, you know, I've got a file location, and how do I get the data that I care out of it? And so part of the problem is, well, if we can locate parts of the file that we need, then we can just read those. But you know, we have this like locate, read, translate issue. And that's really the trade-off that Bob was talking about as well. You know, if you want essentially all the bytes in a file, it's probably better to avoid all the computation that you have to go through to figure out how to do the byte range reads, than just grab the whole thing. There is definitely a tipping point, but the locate, read, translate triumvirate is really what you do when you do want to do one of these partial reads out of S3. I should also point out that, that this is really the same sort of thing that you have on a hard drive. The only real difference between what we're doing in these chunked reads with S3 is that we're changing the code around to deal with this latency question, okay? So, you know, latency is really low with a hard drive and throughput is really high. And so we spent decades optimizing our files for that environment. And then we moved to the cloud where the whole storage system has been optimized to support an incredibly large number of parallel reads. The trade-off there is that latency is really, really high. 70 milliseconds is a long time for a computer to sit around and do nothing. But the throughput is also shockingly high, like 25 gigabytes a second. And like I said, parallelism is massively high because you have these cloud data stores and they're designed to be accessed at the same time by hundreds of thousands of users. It's just shockingly high levels of parallelism that are supported. So the consequences for file formats are that even if we emphasize that we want to optimize for fewer reads, even if that means fetching extra data only to discard it. And so, in fact, both of the techniques that Patrick talked about, and as well as the one that Bob talked about, they both probably fetch, well, even Patrick's probably fetches extra data and then just pitches it on the floor later on. Cloud optimized again, able to fetch lots of data in a small number of reads. That's absolutely key. And like Bob said, he just takes that to the total extreme, just one big read. But we wanted, in this talk, I'm talking about the DMR++ technology and why we developed it. So we want to do these partial reads. So that's where we get OPeNDAP in the cloud and the DMR++. And so as an overview, there are three possible ways to build this in the cloud. And we conducted this study using some support from NASA quite some time ago. We worked with the HDF group, hi Ted, hi Alex, on this, and that's where DMR++ was originally developed. DMR stands for the dataset metadata response. It's a component of the DAP4 protocol, which we worked with Unidata to develop using some NOAA funding now quite some time ago. And the plus plus just means it's got extra metadata, just like C++ is like an extra, it's got like a version of C with more stuff in it. So in the first architecture that we actually looked at when we developed this technology, we did what Erdap does, which is to say, we said, oh, well, this file is in S3. We're going to pull it out of S3 and cache it and work with it locally. And we have a fair amount of data on how that kind of system performs. And in fact, it performs very well in many cases. And then architecture 2, we looked at range gets. So HTTP allows you to get just parts of things. And this was actually added to the hypertext transfer protocol because, you know, when you get a file, but it doesn't quite come all the way, and so you click on the link again, behind the scenes, your client program can know that it's already got the first 10,000 bytes and can ask the server for the remaining, I don't know, 20,000 bytes, whatever it might be. And so it can do these range requests. It can say, I want you to start at 20,000 and go all the way to the end. I want you to start at 20,000 and go to 30,000, for example. So that's actually what DMR++ is doing. It provides the meta information for that. And then the DMR++ software grinds on that meta information and issues the different reads. A third technique that we looked at is actually sharding HDF5 files, actually taking them and pulling them apart into discrete things so that each little piece is addressed by a discrete URL. It actually performed in many ways comparable to the DMR++, but it can degrade under certain circumstances. It's kind of a long discussion, but there is a paper, a trade study that compares these three, and I'm pretty sure that's open and you can get access to it. Comparing these designs, transferring the whole file can be fastest when you want to get all the data. This second technique, which we call virtual sharding, partially because it sounds cool, preserves the original data file, which is a potential big win. If you don't have to reformat a lot of data, there's a lot of processing you don't have to do, and the potential for mistakes that will be costly to unwind as well is avoided. You avoid the potential for the mistakes. It still allows subset in place, so that's cool. But unfortunately, to be performant, virtual sharding has to be pretty heavily optimized. You have to do a lot of work to make it work right. True sharding is actually what ZAR does. ZAR has a different URL for each of the different little chunks. And well, there's pluses and minuses to that as well. But unfortunately, when you actually shard the thing, it's very difficult to combine the different chunks that you might be able to transfer optimally. It's very difficult to do that. But this is a session partly about for data providers, and what I want to talk about right now is the DMR++ setup. And what you need to do, and this is one thing about DMR++ that's kind of a fly in the ointment, you have to compute these files ahead of time. Okay, so before DMR++ capable software is used to read data from the file, you have to have pre-processed that file and built this metadata object. When I object a metadata object, I'm using computer science speak here, but it's just a bunch of XML sitting in a file. Okay, but you have to do that a priori. So Ted asked a question, would it be better to store that in a database? And there are some cases where you might want to do that. So as I mentioned before, the key thing is that because HTTP supports range get operations, we can get just these chunks. Now, an optimization or several optimizations that we employ are using parallel reads, which enable us to collapse some of that latency time. If you need to make 10 requests and you make them serially, you pay the latency time in the front of each one. If you make the 10 requests in parallel, you effectively pay the latency just once. We decompress chunks in parallel. So as we get chunks, we throw them into a queue. Other code is pulling them out. We run as many decompression operations as we possibly can. And then we use this super chunk notion where we take adjacent chunks and we transfer them as a single unit. And that's a thing that is possible with virtual sharding that's not possible with the actual sharding. There are some other tricks. We can use DMR++ to aggregate across many objects. And also, we can use this on spinning disks, and it can be really, really efficient with spinning disks as well, which might sound sort of counterintuitive, but what you're really doing is you're paying the time necessary to read all the metadata upfront once. And in a data server, you can hold those metadata in RAM, and you can cache them in RAM so that subsequent requests don't even need to process the XML. So in classic form, I've gone over time. I think I was supposed to stop myself a while ago, but what I want to do is I want to show you just a couple quick things about the server. And so I'm gonna stop sharing the screen as I am now, and I'm just gonna share my whole screen, which is always a risky move, I'm told, but I'm gonna do it anyways. And we're just going to go through a couple of quick things here. So So here in this window, I'm going to show you our form interface. And actually, you know what I'm going to do? I'm just going to show the one window because it's going to make it a lot easier for me and my claim for y'all. Like anyways. There we go. So let's take a look at some Mera-2 data. So we're gonna if we go back here and we go to this page here. I don't know, can you guys see this page?
Yeah.
Yep.
Cool. So this is a list of OPeNDAP servers that EOSDIS provides. And I just scrolled down and I said, hey, look, here's a Hyrax server and it's serving Mera-2 data. So if I just grab this link right here, I can just bop over to it, and I'm going to save us a little bit of time by going here. And this is the default page of Hyrax, and here we can see in this corner down here, we can see the version number of the server, for example. And here we can click on Mera-2 monthly, and we can drive down into the Mera-2 monthly and take a look at this M2C0 NXASM data set, or it's actually, this is model data from 1980. And so here, this is the page that Hyrax shows when you get down to a data set. And so you can see the data set link is right here where I'm hovering with my mouse. There's a last modified time here that says this was last modified in 2019, July 8th. Gives us the size in bytes, and it gives us a bunch of metadata links we can click on to get various information. There's also another link set over here called viewers. So there's a set of web-enabled viewers we can take a look at. Here we can click on this, and what we'll do is we'll drop into it and we'll get this form interface, which is what I really want to demonstrate. And part of the reason I want to demonstrate this is not the coolest interface that we have for OPeNDAP. This is the least cool interface, maybe in some sense, but it's also the one that a lot of people wind up at. And it's really important because it provides all kinds of tools that are useful for looking at information. So we've got the data set name here, but we've also got this URL, which is the URL to the data set that you would use if you were pasting this into Matlab or some other tool, okay, like Panoply, for example. Here we've got global attributes we can look at, and we can expand them, and we can read about this data set. So history, it was updated to remove area on March 21st, 2016. There's some other things. It adheres to the CF1 conventions. You can see that right here. All sorts of good stuff. In fact, there's also a whole bunch of geospatial information that's right there. Oops, but I just closed it up. So if we close up the global metadata, now what we're looking at are all the variables in this file. They're right here. And we can see, for example, that they also have attributes, and we can expand that information. And this tells us the scale factor and all kinds of things about this. We can choose to take a look at the values. So we can click on this checkbox and we can subset this. So if we go, like, if we do something like this by 10 and this by 15, what we've done is we've said, hey, I want to get a subset of these data, and then we can go up here and we can get this as ASCII. Now, keep in mind, I'm at a hotel right outside of Glacier Park. I'd like to take this opportunity to thank my wife for donating the morning of our vacation to my session. But here, what we've done is we've just grabbed an ASCII representation of these data. And this, sort of fits on the page. That was sort of the beauty of subsetting, and gives us a notion of what we're looking at, a bunch of zeros and then some floating point values. So, interesting. notice that the long name of this variable is fraction of ocean. So that's cool. Suppose now, based on what we've seen here, we say, yes, I'd like to see these data in Matlab. So there's some more stuff that I was going to show you with this, and I actually have a 10-page online tutorial about this interface that we've written up. I'm going to make that link available to people who want that, but I'm going to just switch over to a Matlab window now. So I'm going to stop sharing this one, and I'm going to start sharing Matlab. And we're going to take a look at what it's like to look at these data in Matlab. So here we are in Matlab, and what I've done is I've dropped a URL in here, and it happens to be the URL that I pulled out of that web form. Let's see, I'm on a laptop, so you can't really see so well. So I'll just scroll. It's sort of annoying for that to happen. But you notice that this URL ends in .nc4. So it's the URL that was built up by the little form interface. So Matlab has a great interface that works for netcdf files and OPeNDAP. And in fact, if you Google Matlab and OPeNDAP, you'll get to a kind of a nice page where they talk about this, and they talk specifically about OPeNDAP, but they don't show any demos with URLs. So I'm going to show you a demo with a URL. So there's NC display, and now this you can see this is a true demo material here. So off we go. We drop in this URL, and it's going to go out to the data set, and it pulls a whole bunch of metadata across. NC display it does not collapse things the way our form interface does. So here you see the attribute information I was talking about before, conventions, CF1. We scroll down here. Here's information about the geospatial location of the data and the resolution information. Its latitude resolution is 1/2 degree. Its longitude resolution is strange. And because we're running a little bit short on time, I'm going to kind of cut to the chase, and we're going to grab that FR ocean variable. We're just going to get the whole one, okay? And I have in another window that I'm secretly hiding from you, I have these commands, so I can easily cut and paste them. But here, I'm using NC read to read from the URL and this FR ocean variable. And you can see over here in the workspace where variables pop up. And again, remember, I'm here at a hotel. so it's a bit slow, but there we got it. And one of the things you'd notice is that it's 576 by 361. So if we went back and looked, you would see that is actually longitude versus latitude, and I want to see latitude versus longitude. So I'm going to transpose the variable, and I didn't have this one pasted. Misspelled the word ocean. That's most impressive. Oops. And so we've transposed it. And so one thing we can do with the transposed version is we can click on it. We can go over here to plots, and we can get a contour plot, for example. And we can actually see that we've got data down here. Now, in a more complete demonstration, I would show how to subset this geospatially. The more complete demonstration is also available online. It shows how to take a look at the various metadata and compute the offsets, the initial subsetting, to get just a region like the Northern Atlantic. But I'm out of time, so in true gong show tradition, I have to pull myself off the stage and ask for any questions that you might have. And I see that there's a number of things that have appeared in chat. So, questions? There's got to be some sort of question somewhere. Oh, can we see you couldn't see the contour map. Oh, that's very sad. Here, I'll just share the whole screen. The answer is yeah, you can't see the contour map. So there it is. And in fact, you can go around and you can click in it. You can look at different data values. I mean, what we've done is when we read the data with Matlab, we're not making a file and transferring the file and then reading the file. We're actually going over the network and pulling the data values over. So if I were to come up with a subset request, which I could also easily have typed in here, I would only be pulling the subset of data across. And that's actually the original notion of what OPeNDAP was supposed to do. But I should stop here and I should take questions. If you are asking me questions, I can't hear you.
Hey, James.
Hey, Ted, I can hear you.
Good. I think one of the nice things about the demo that you just gave was it showed that lots of attributes can exist in these data sets, and they can be pretty helpful for understanding what FRO means.
Yeah,
but,
exactly.
And could you refresh my memory on DMR? The attributes for each data set and each group are also included in DMR, is that right?
Yes, that's correct. Yes, the DMR holds all of the attribute information for the entire data set. And DMR++ simply augments that with the offset and size information for the different chunks. So yeah, I mean, we could talk about two different kinds of metadata. Every data set, every science data set has two different kinds of metadata, or two sets of metadata. One is structural information, which is sort of the computer sciencey part of the data set. What are the data types? What are the names of the variables? What's the dimensionality? And then the semantic information, such as what's the long name for this variable? What are the units that it represents? Is it degrees Kelvin? Is it a fraction? So on and so forth. All of that metadata is held in the DMR. In DAP2, we separated those out into two discrete responses. Other questions?
And is the DMR is still XML, or is there JSON representation as well?
Right now, the DMR is still XML. There certainly could be a JSON representation, and in fact, HireX does provide it will spit out JSON for various kinds of things, and also coverage JSON for different things. Although the JSON responses are actually primarily ways of accessing data values, but the data values come packaged with the metadata in JSON as well. So we're really thinking about how best to optimize DMR for some of these new data sets, which can have 1,000 variables in them, something that we never really thought about. Other questions? You know, technically, I think we're out of time. I'm not sure if we get penalized for going over time or not, but
you're going to get penalized by me because I need lunch. Come on now.
I would say it's a good time.
By you?
It's a good time to say if you need to go, we welcome everyone getting a solid break in between their sessions if they need food, an exhale, a leg stretch, etc. If anyone would like to stay on to continue chatting, we will keep this window open so you can keep the conversation going. So I won't end the session, but I welcome anyone that needs to leave to do as you wish.
Cool.
I just needed to get good lunch, Jim. That's all.
I had another question for Bob. Bob, you know, you mentioned that there's a lot of earth science data in tabular form, and I agree. You have much experience with HDF5 compound data types, which is sort of the HDF arrangement for such data?
Yeah, actually, I just started working with that for one group, and so I added to the most recent version of Erdap the ability to at least read that data. So yes, you can read it. I don't know what to say. For me, I found it not so useful. At least what they had done with it was not so useful for me because they were using it for what I would have used standard gridded data with separate variables. And so by combining it, I lost the ability to read just one variable at a time. And I was forced to plow through what appears then as a sequence of data. And the plowing through involves parsing, not parsing, but you have to request the next essentially row, and then request the variable from that. So there's a lot of individual requests to roll through that data, and for the data sets we were working with, that was actually not useful. But I can see that for more traditional columnar type data, then it would be a normal thing to do. But at least for the purposes we used, it wasn't so good. But again, who knows? Different purposes.
Thanks.
Oh, Nathan, your hand has been raised for a while. Do you have a question?
No, I had my moment in the sun there. It's all good.
Well, thanks everybody. Really learned a lot during the session.
Yeah, James, Patrick.
Thanks, James, for pulling it together. And
Yeah, no worries.
have a good vacation.
This was great. Yeah, this was great. Yeah, and I really want to thank Bob and Patrick for their work. I mean, it's great. I mean, not just their presentation, but their work, which is substantial, and also their presentations. It's great to talk about this stuff, and it's great. Thank you very much. I really appreciate everybody attending. And if you have any questions, you can always email OPeNDAP, support@opendap.org. You can always email us. We'll try to get back to you with something intelligent. Thanks.
See you later, James.
Bye.
Bye-bye.
Thank you all. Thanks, James.